All right. Sorry about the late start. Chris is away this month, and he usually does all our AV, so we're kind of flying a little bit by the seat of our pants today. So welcome everyone to the July meeting of the Royal Astronomical Society of Canada Ottawa Centre. We've got a great program for you today. We're going to start off with Dave Chisholm in Ottawa Skies, Al Scott giving us a 10-minute astronomy news update. Paul Klauninger will be giving us an Imager's Corner presentation. And then after the break, we'll have Simon Hanmer up giving us the second part of his talk on the origins of the solar system. And we'll close off with observations, observation challenge, and then various announcements. All right, so these are our new members for the month. Let's give them a warm welcome. All right, members in the news. So we had Ian Halliday passed away recently. He was a long-term member of the Ottawa Centre. As you can see, he took on many roles with the Centre and National. He'll be missed. So we just had our GA, the GA in Calgary just happened, and as I mentioned last month, Mike Mognan was awarded the Kilac Award for public outreach. So congratulations, Mike. Here's a photograph of him getting the award. All right. Doug Luama was featured here in this Sky News article.
If anyone's interested in how I took the shot or the processing, I just posted recently on Solar Observing Forum on Cloudy Nights website.
Okay, thank you, Doug. So thank you to all the volunteers who set up on July 1st as well. Here are some of the images that were taken at that event. Oh. Just one image. All right.
Yeah, exactly.
You're up next there. So you just have to.
I have no idea what I'm doing. Oscar just told me I'm doing this. Breaking news. Yes, breaking news. The government has decided, it's incredible that it doesn't like green laser pointers. Hello? How do I know? Do I look like you know that? All right.
Something wrong with the lavalier.
Hello? Oh, what? Oh, okay. Anyway, laser pointers. And I used to like Mark Garneau. Anyway, handheld laser pointers are now, well, basically they're in the same category as lasers at a Led Zeppelin concert. Oh, never mind. Oh, it's still, man. Anyway, there are some pretty hefty restrictions on using even green laser pointers, the standard handhelds. As you can see down there, anything over a milliwatt requires special permission. Yes. Wait a minute, young Jedi. Switch the channel.
He's got a tune you in.
Come on, Tim, I'm going to come after you.
It's a lousy. I like it. Okay, yeah.
Yay, Tim.
Yeah, you. Yeah, when I blow something up and Oscar. It's a good thing I'm doing this, Oscar. Anyway, that's what. It's all his fault, you know that. Okay.
It's entirely my fault.
It is entirely his fault. So the bottom line is, if we take a look, using laser pointers above 1 milliwatt, which means practically anything that is useful.
Let's give up on the mic.
Yeah.
Using laser pointers above a milliwatt, which is really pretty unuseful. In most urban centers, anywhere near an airport, you pretty much can't do it. And the fines are reasonable. Just having one outside and being caught with it is a $5,000 fine. And we still have all the standard stuff about being dumb enough to aim one in an airplane. Which none of us would be stupid enough to do. The bottom line is, if you look at the Ottawa area, pretty much any place we might want to use a laser pointer is in the strictly verboten zone. So in order to get around this, one must file a permit to get permission to use a laser pointer, even a laser pointer. The form is the regular form that one would use for something like a Led Zeppelin concert, which requires you to calculate safe dazzle distances and power ratio levels and every other paragraph and such like. As it turns out, an acquaintance of mine spent some time, most of his career, working with lasers. So he walked me through the form and explained what the gobbledygook meant, and worked out an example for typical laser pointers. So we may be able to get permits for at least carp. I don't know, but we can at least give it a shot. Bottom line is, anywhere in the Ottawa area, if you take a look at that map, if you do decide to go out and do any kind of an outreach thing, and you've got a laser pointer with you, stick it in your pocket. You will probably be okay, but if somebody does actually decide to rat you out, you're looking at a $5 grand fine. So it's just not worth it. So in its inimitable way, National has said they're on top of it. And of course, I trust them implicitly on that. So they will undoubtedly have a proper system for this sometime by the next centenary, but don't count on it. Basically, no laser pointers outside. Sorry, guys. So here we go. All the places we might want to do it, we can't do it. And incidentally, just to add insult to injury, on the Transport Canada webpage describing all their bits, they refer you to go out to the Royal Astronomical Society of Canada to find guidelines on using laser pointers safely. But we don't have an exemption to use them, unless we're out in the boonies. Never mind. So there you have it, ladies and gentlemen, and bipedal humanoids, brought to you by our government. Yes. I might not have an answer, but ask away.
I'm just chatting with John here. First, it doesn't have an airport, but you had a...
There's a landing strip there.
Okay.
Yep.
So that the Iron Prior does have an airport, and it was not covered.
Don't ask. This is the official stuff from Transport Canada.
Well, it must be right.
Oh yes, it must be right.
Right, like Iron Prior is right there.
Don't tell me. Tell Garneau.
But there's an airplane factory there.
Well, see, that's it. And there's a killdeer behind the Blues Fest, so we can't have a laser pointer near that either.
All right.
There we
Thank
go.
you, Tim.
So,
any more questions?
you're allowed to have laser pointers inside. You're okay for that?
But can you point them out a window while you're inside?
No.
No. All right.
No, if you live off the sticks, you're saying that we're not allowed to use it.
Check Transport Canada, but you'll find that most areas around Ottawa are in the prohibited zone. You have to go way out.
Okay, maybe Tim will take some questions at the break.
Again, it's the same deal. If you are caught, you're looking at a $5 grand fine, and the police have the right to lay it on you on the spot, as in pay up now or.
Go to jail.
Thank you, Tim.
So basically, good visa. I don't know.
They'll cut
Depends
you away.
whether or not you shine a laser pointer in your eyes.
All right. So now we've got Dave Chisholm with Ottawa Skies. This one.
Okay, folks, I'll try to speak loudly here. So let's take a look at the Ottawa skies for this month. So this is the moon phases for the month of July. Full moon is on July the 27th. If you happen to be in South Africa or Australia, there is a total lunar eclipse on July the 28th. I happen to be there, so I will bring back some pictures. This month we have the Delta Aquarids meteor shower that coincides perfectly with the full moon. So good luck. Let's see, about 20 meters per hour is the average, and it peaks the night of July 28th and the morning of July the 29th. And they'll radiate from the constellation Aquarius. Mercury, these are the rise and set times. Greatest eastern elongation is on July the 12th, which means you may, if you're in the right location, look for it low in the western sky just after sunset. Venus is visible all month, just after sunset. Mars is visible all night. It's rising around 11 o'clock at the start of the month, and by the end of the month it's going to be rising at 10 to 9. It's at opposition closest to the Earth on July the 27th. You're going to hear some really interesting articles and miscommunications around that. You know, some people say it's going to be as big as the moon. Well, you know, that's not the reality, but it's always interesting to see how the media covers these things. Jupiter is visible all night. Saturn is also visible all night. Uranus is visible in the early morning, and Neptune is visible in the early morning and late evening. And there's your cartoon for the month. Thank you.
Rob, can we dim the house lights a little bit, please? Hey, can we dim the audience lights? Thanks. Rick?
Hi. So, if you were all paying attention, and I know you were, to that interesting presentation, you will have noticed that Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune are all visible throughout most of the night. So, this is an opportunity round about the middle of the month when Mercury is at greatest elongation east. You can actually get out in one night and see all the major planets in the solar system on one night. How many people have ever done that before? Okay, so there are a couple. Good. So, Mercury after sunset, Venus, Jupiter, Mars, probably you want to be more towards midnight. If you get up like sort of midnight, 2 o'clock, you can see Uranus and Neptune. You'll have to go online probably to find charts for Neptune. Uranus is visible naked eye. Hardly anybody has ever seen Uranus naked eye. To do all the major planets in the solar system right now is a lot easier than it used to be because Pluto is no longer a major planet. However, it is also up in the sky, so if you have a 10-inch or 12-inch telescope, you'll be able to see it as well. And the other excitement, if you want to even make it a more complete set, the asteroid Vesta this month is going to be naked eye, about 5.3 magnitude. So if you get out in dark skies, you'll be able to add it to your tally as well. So I want everybody to come out and come back in August and tell us how great it was to see the whole friggin' solar... Oh, don't forget, do what I did. You start counting up the planets and you keep coming to 8. Where's the other one? Oh yeah! I'd forgotten to look at the Earth. So, go out and observe.
All right, Al.
Okay. Good evening, everybody. So I'm here to give the 10-minute astronomy news. And whenever I go out to this, my 2-year-old son Rigel says, "Oh, Daddy's going to go sing to the moon." And I didn't know why he was saying that. It's like, it's interesting the associations young kids make. He actually saw me at the GA standing up there talking about the lunar eclipse, and there's a big image of the moon on the screen behind him, and I had a microphone in my hand. And of course, he knows that with a microphone, it's a karaoke machine in the house that the kids like to play with. So he thought I was singing to the moon. So whenever I go out here now, "Is Daddy singing to the moon?" "Yes, Daddy's going to go sing to the moon." So, this month's news item, the Tarantula Nebula and the large Magellanic Cloud, pictured here, or 30 Doradus, is one of the largest star-forming regions in the local group of galaxies. Recently, astronomers have looked at the stars and tried to do a survey counting the large and the small stars, and they believe that it's forming an unexpectedly high number of large stars. In fact, there could be stars in this being formed in this nebula up to 300 times the mass of the sun. So I want to report on some new research that recently has been occurring that also suggests that in certain star-forming regions, there's forming more larger stars than astronomers originally expected. So for decades, astronomers have used something called the initial mass function, the IMF, not the International Monetary Fund. And this is basically a function that says stars are formed in the same proportions as a function of size everywhere in the universe. And this, they think basically it's because of the physics of collapsing gas clouds. So you have a nebula of gas, you have some turbulence, you have a bunch of cores that have a little more density than some others, and they start the collapse process, and the gas will preferentially collapse into these cores and form a distribution of stellar masses. And this is kind of like a log normal function. So you have very few extremely large stars and a lot of small ones, and it follows also, you know, the main sequence diagram of you know, giants down to dwarfs. This distribution was thought to be universal. Back in 1955 was the original paper on this distribution. So astronomers have based a lot of their estimates on this initial mass function, often used to estimate the mass of distant galaxies based on the brightness, the integrated brightness of all of their stars. We believe then we can, using this initial mass function, and we know how bright and what the colors are and how big they must be, we then estimate based on this function what the mass of the stars in the galaxy will be. If this turns out not to be true, and 30 Doradus seem to be proving the exception, then astronomers would have to revise many of their estimates of mass of distant galaxies and their classification of how quickly stars formed in the history of the universe. So the study I'm going to be looking at here was done using the ALMA telescope, the Atacama Large Millimeter Array. The focus of the study was 4 galaxies more than 10 billion light years away. And you can see them pictured here, imaged by the ALMA array. These galaxies are called Starburst Galaxies in that they're forming lots of stars very quickly, and their brightness is exceptional in certain wavelengths that let us know that they're actually forming a lot of stars. But these are also very dusty galaxies. So they're very bright, small galaxies, very distant, but they're also dusty. And what that means is that the ultraviolet light, the visible light, even the infrared light is being absorbed in dust, and you can't see them in those wavelengths. It's re-emitting all this light in the millimeter and microwave regions. Thus the ALMA array is able to see them and image them. Now what these are images in certain particular wave bands which correspond to what you call isotopologues of carbon monoxide, CO. So carbon monoxide is a molecule with 1 carbon atom, 1 oxygen atom, and isotopologues have odd or different numbers of neutrons in their nuclei, and what that does, it makes the mass different, it makes the frequencies at which they vibrate a little bit different than the most common forms. So usually you have C12, O16. Well, the upper row is 13C16O, so a little heavier atom of oxygen with a normal mass of, or a little heavier carbon with normal mass of oxygen. The bottom row is normal carbon with 18 oxygen, so a heavier oxygen and a normal carbon. And these emit at different wavelengths, and so ALMA can measure the different wavelengths and measure the abundance of carbon monoxide at each of these wavelengths and can compare them. And the reason this is important is that the chemistry of carbon monoxide doesn't depend on the number of neutrons in the atoms of the carbon and the oxygen. These things form at the same rate and in the same circumstances no matter what the isotope of carbon or oxygen. So the chemistry and the physics of the formation of these molecules is pretty constant in the interstellar gas. These things are formed in stars and blown out in nebula as the stars die or if they go supernova, and mix in the interstellar mediums of these galaxies. And the interesting thing is, 18 oxygen is only made in massive stars. So this ratio between 18O and 13C tells us the ratio of massive stars, supermassive stars, to the ratio of more normal massive stars. And so what the astronomers did was they modeled what a normal galaxy should produce in this ratio, knowing what they do about stellar evolution, stellar lifetime, evolution of stars, brightness of stars, wavelengths. It's a very detailed model, how these things are mixed in the interstellar medium, and they make a prediction as to what the ratio should be. And it turns out that the C18O is much more dominant than it should be. The ratio is wrong. What this means is that these distant galaxies are forming more massive stars and less smaller stars than the initial mass function that astronomers typically use. So if the measurements hold up, then what we dubbed starburst galaxies in the early universe aren't actually making as many stars as we thought, because the bigger stars are actually giving out a lot more light than the smaller stars. So there's a lot fewer stars being produced than astronomers first thought, if this particular result holds up, and it seems like it's been well researched. Obviously there'll be more studies. Oh, I didn't say one thing. The reason astronomers could see these 10 billion light year away galaxies is that they're actually being lensed gravitationally by a foreground galaxy group. So they were able to pick these things out using a gravitational lens from so far away that they would never actually have been able to see it without that help. So there's a fortuitous alignment of a foreground galaxy group that allows them to make this discovery. So this result, if it holds up, means that methods of estimating star formation rates might be wrong. Cosmic star formation history, estimates of star formation abundances, and cosmology are going to have to be revised based on these results. In fact, what it tells us is that the initial mass function is not universal and depends on environment. The physics of these core formations and the statistics isn't universal. And that means that astronomers are going to have to think a little bit more and change their models somewhat to adjust, to take these results into account. So that's my last news item. I wanted to leave you with this, though. This was an XKCD comic that I saw. It's actually about the JWST telescope. They recently revised the launch date to 2021. And this is a graph of the current date versus the planned launch date. And the red line is a fit to the planned launch date. So the good news is that the slope is less than 1, which means eventually it will launch. Astronomers believe that as we approach the actual launch date, that the expansion of the schedule should be slowing. But recent observations suggest that the expansion of the schedule is actually accelerating. So there may be a Nobel Prize in this. Thank you.
All right, up next, we've got Paul from Mayor's Corner.
Super. Can I use that?
Yeah.
Well, yeah, we're
as long as
indoors.
you're not outdoors.
Okay,
And you advance the slide and go back.
super. Thank you.
Speak
I'll
loud.
talk louder. Oscar, that means I probably have to talk slower. Just giving you forward. All right, good evening, everybody. Oscar asked me to if I could do an Imager's Corner talk, and told him I was totally busy, and he forced me, so that's why I'm up here. Thanks, Oscar. This is a follow-up to a couple of talks that I gave within the last year on getting into imaging, kind of our astrophotography 101 and 102. So tonight, we're going to talk about dark frames. If any of you recall that those sessions, I mentioned that, you know, go out and shoot and learn your camera, experiment with it, and take some dark frames, and we'll get into those later. Well, later has come. So I'm going to explain a little bit about dark frames. I'm not going to, there's a bunch of calibration things that we can talk about, but I'm going to focus tonight on dark frames because these are, this type of calibration that you can do to your images is probably one of the ones that will have the greatest effect. All right, so where do we start? Today's cameras, and my talk will focus on mostly DSLRs because that's what most of you are shooting, and those that are shooting with CCD, astronomical CCD cameras probably already know everything I'm going to say here. So we'll focus on DSLRs, and today's DSLRs are amazing devices. The sensors, the electronics behind the sensors, the processing that goes on, much greater quality than even just a few years ago. The sensors are a lot less noisy than they used to be, and there's no more amp flow issues, all of that kind of good stuff. So bottom line is that they can produce some pretty darn good pictures under a variety of conditions. But no sensor is perfect. There is no such thing as a perfect sensor. They all still generate a degree of noise, and that's the nature of the beast. They're electronic devices. You're sending electricity through circuits. That creates all sorts of currents and fields and things. So you do get some noise generated from the actual operation of the equipment. But for most of photography that you do, especially daytime stuff, when you're vacation shots and that, you wouldn't notice that. You wouldn't notice the difference. But with what we do in astrophotography, it's a different story because we tend to shoot in ways that are very different than the cameras that were originally designed to do. So each camera, any camera that you can imagine, electronic camera, has a bunch of things going on inside that will generate noise, and for different reasons. You can see here there's bias level, and there's dark current, and just the sensor's raw sensitivity to the light that's falling on it. And the important thing to remember is that these little variations that occur within the sensor don't just occur from one sensor to the next, but they occur within pixels in one individual sensor. So each sensor is like a fingerprint. It's unique. It has its own characteristics of these currents that it generates, and the noise that creates in your image. So what we try to do by calibrating our images is try to address these sources of noise because they're extraneous. They're not part of your picture. So if you can remove the noise, you actually get a truer representation of what it is you're trying to image. For some things, it's not that important. I mean, for some type of imaging, you wouldn't notice much of a difference. For other types of astronomical imaging, it becomes extremely important. For those of you that might remember the shots that I showed you on the gravitational lens, and I had to take a lot of this into account because the signal that I was chasing was just above the noise floor, so I had to deal with the noise to try to ferret out the details. So it can get pretty involved, but you don't have to, it's not an either-or thing. You can look at trying to experiment with calibrating your images by taking it one step at a time. So highly suggested is that you shoot in RAW, for one thing. I did mention that in our previous talks. The RAW format contains all the data that your sensor captures. JPEG is which is the other common format that's available to you through your camera, is a compressed format. It generates its own noise artifacts, and so it's not as good. It's also only 8-bit compared to typically nowadays 12 or 14-bit in images in your coming from your camera. You can calibrate JPEG images, but it's not nearly as effective. That's the bottom line. So computer storage is cheap these days. Shoot RAW, because as you learn things, you also tend to go back and say, let me try this because I just learned this and I'd like to try that on the shot that I took a year ago or so. So shooting RAW is a good idea. Most cameras allow you to do both. Actually, I do both because JPEGs are quicker to preview. So for tonight, I'm just going to have a look at dark current. So you've heard many of us mention, those of us that are into it, about dark frames and dark frame subtraction. That's what I'm going to talk about tonight. All right, so when we look at an astronomical image and its histogram, let's see if I can get the laser right here without getting fined. What we see, sorry?
You're indoors.
Excellent, super. I don't want to burn a hole through the ceiling or anything. So we look at an image, and I mean this is obviously an astronomical image, but the same holds true in terms of the histogram for daylight subjects rather. What the histogram tells you is that it's a graph of the distribution of your pixels. Okay. At this end of the histogram, these are your dark pixels, and these are your white pixels, and everything in between is in between. It's not totally black, and it's not totally white, which means saturated. It's various levels. And in this picture, you can see there's a lot of dark here, so the pixels tend to cluster towards the left hand of the histogram. The vertical axis shows you the number of pixels at any one particular level. So it's just a map of distribution. For daytime photography, your histogram tends to be, the peak tends to be more centered. So this is a normal astronomical picture. And in an ideal world, if you were to take your camera and put a cap on the lens or your telescope and take a picture, what would you expect in an ideal world? Nothing at all, eh? Totally black. No light is hitting the sensor. And so what I did is I just created a black frame in Photoshop. Every pixel here has the same value. It's 0. The whole field is black, as you can see. And the histogram reflects that. You can see the histogram shows no pixels anywhere except this one thick line right at the 0 point. That's the ideal world. But as we know, the world isn't ideal. When we take a real dark frame, we put our cap on our lens or our telescope and we snap off a picture, it looks pretty black, right? It looks pretty black, but you can tell, the histogram tells you that it's not entirely black. You can see there is something beyond 0 or totally black in this, although it looks, obviously there's not much else. It's just a relatively black field. When you see the whole image like that, it looks pretty black, and you think, well, what's he worried about, right? What happens is if we stretch this histogram, in other words, if we concentrate just on the areas at the left, we actually see, what I want to show you. That's what it actually looks like. You should try this with your own camera if you're curious. Just take a dark frame and take it into something where you can stretch the intensity, the brightness levels there, and you'll see this pattern. It's very, very dim. I mean, as you see, these levels here are down less than 10 from 0. On the previous scale, the full scale was 255. So we're talking about very dim stuff, but it's there, and it becomes part of your picture. And so it's actually taking away from what it is you're trying to photograph because you're introducing stuff that's not really there. We want to get rid of that. And that's why we shoot dark frames. Okay, that by shooting dark frames, we can address, at least in part, some of this patterned noise that's generated as a function of the camera's operation. So just a few bullet points here on that. I won't spend a lot of time on it because Oscar is undoubtedly checking the clock here. But a dark frame is essentially an exposure that's the same duration as your light frame, the object of interest, same ISO, but with your lens or your telescope capped off, so no light is entering the sensor. And for those of you that try this and are shooting with DSLRs, I don't know if I mentioned that or not, but if you're going to do this, you should also cap the rear viewfinder because light can actually leak through from the rear viewfinder and find its way onto your sensor. Okay, so if you're shooting dark frames, cap the back as well. You'll notice on your camera strap, if you bought your camera new, there tends to be a little black square there attached to the strap there. That's what that's for. It's actually, if you remove the cover from the viewfinder, you'll find that little black cover fits directly on that, and it allows you to block the light from entering that viewfinder. So with DSLRs, you can do some dark frame subtraction. The easiest way to do it is by using a function that's built into a lot of the sort of the upper end or medium end DSLRs. There's a function, and especially I'm most familiar with Canon and Nikon, there's a function called long exposure noise reduction. Check out that settings, because what it does is that if you take a 5-minute exposure with your camera, it will immediately, after that exposure is complete, it will take its own dark frame. It will keep the shutter closed, so you actually, if you're doing that technique, you don't have to worry about capping your telescope or your camera, because the shutter will be completely covering the sensor itself, and the camera will then expose its own dark frame for the same length of time. All the other parameters are the same, and it will do the subtraction on board. It'll process that, and the image that's saved to your chip or to your computer, if you're using one, is your light frame with one dark frame subtracted. It then can make a huge difference, especially under conditions as we've been experiencing them lately, because the noise generated by your camera is sensitive to temperature. Okay? So dark frames have to be taken at the same or very close to the same temperature as the light frames for them to be effective. And by taking by taking your dark frame right after you take your light frame, chances are the sensors are going to be roughly at the same temperature, unless you've got some really wild temperature thing going on. The disadvantage with using that technique is that it's only using one dark frame. Okay, it's taking one dark frame, subtracting it, and it will be quite effective at reducing the noise. But there's also a random component to the noise that it doesn't take care of. Okay, this is the pattern noise. You saw the kind of the pattern that was in the. Actually, if I can go back, you see the kind of the pattern there. That's starting to form in the background. It's not just random. I mean, there's random noise speckled throughout this, but there's also a pattern that's somewhat obvious. It'll only a single dark frame will only deal with the pattern. It won't deal with the random noise, because that changes from image to image to image. So the second technique, this is a bit trickier with DSLRs, is to shoot a bunch of dark frames, because then later you can stack those to get an average, and it will help to deal with the random noise as well as the pattern noise. The problem with doing that, you say, okay, well, I'll do my darks after I finish my imaging session, or before, or when I get home. It doesn't work that way, or it doesn't work that way very well, let's say, because if you're out for 3, 4, 5 hours, as many of us are when we do this stuff, chances are the temperature will be different. And as I say, that noise is sensitive to temperature, quite sensitive actually, just to even a few degrees difference. So you really need to get, ideally you want those dark frames to be at roughly the same temperature. But if that's not the case, I mean, the downside of shooting, a bunch of darks in the middle of your imaging session is that you lose that time when you could be imaging the live stuff, right? And especially in these months, that night window is pretty short. So it's a good idea to use the alternative and shoot them either after or before, but then you have to recognize that the temperatures will likely be different. So what you can do, but this requires the use of an ancillary program, I've mentioned a few down at the bottom, is that you can use these darks, and then if you have a program such as the ones mentioned down there, they'll actually use those darks and scale them so that they're appropriate for use on your light images. Okay? It's a little bit more involved. With astronomical CCD cameras, this usually isn't an issue, because you can, one of the huge advantages of an astronomical CCD camera is that they have active cooling working on those sensors. They have Peltier coolers on them, so that you can regulate the temperature usually down to 1/10 of a degree Celsius. That permits you to shoot your dark frames with high precision and at the same temperature as your light frames. But as I say, with DSLRs, you don't have that luxury, and it's important to shoot the dark frames, especially under the warmer conditions, because that noise is sensitive to temperature. All right, so let's see here. The other advantage of doing the sets is that you can build a library of images. So you can shoot your darks either before or after or during, and then just collect those and then sort them by temperature for use later on. When you do the internal one frame dark frame subtraction in your camera, that dark frame isn't stored on your chip. It's integrated into the exposure that the camera writes to the chip, so you don't get to use that again. So being able to build a library is a useful thing because it'll save you shooting darks later on. And the more of them that you get, the more of them you can stack together. The more of them you stack together, the better you deal with the noise. Okay? All right. So if you want to shoot these dark frames, as I mentioned, you can do the technique, the individual technique. That's a good place to start because take a few pictures with your camera and try that technique. You'll see the difference will be noticeable, especially on warm nights. So check it out, and that may pique your interest into trying the somewhat more elaborate scale of a setup of shooting numerous of these pictures. As you can see from the line down at the bottom, the random noise that's integrated in this, as I say, only stacking that will help to reduce that random noise. The random noise is decreased by the square root of the number of images that you take. So, in other words, if you average 4 dark frames together, you'll actually reduce that noise level by a factor of 2. If you shoot 16 of them, you'll reduce it by a factor, down to a quarter, by a factor of 4. So you can see there is a law of diminishing returns. You don't want to, unless you've got a lot of time on your hands, you don't want to shoot 100 of them. It's nice to have, and that's one of the advantages of collecting a library, because over time you can actually get quite a number together, and then again, your calibration processing will be more effective. All right. So you wonder, how can I tell the temperature of my images if I'm just starting into this? Well, most of the programs that I mentioned, things like, PixInsight, MaximDL, dedicated, AstroArt, Images Plus, dedicated astronomical programs will read that information from the information that your camera embedded in that file when it took the picture. There's something called an XF header, or FITS header as well, that the camera writes this to a certain specification. It records this information. One of the pieces of data that it records is the temperature of the camera sensor at the time that the exposure was taken. So that's what you want to know. So a piece of freeware, if you're reluctant to spend a lot of money on a dedicated high-power program, I've mentioned this before, the Earphone Viewer. It's a free download, great little quick image editing program. It will also read the XF information. You can see you just essentially click on image information, that'll open that window, then you click the XF info box, and you get a secondary window which allows you to scroll down. And lo and behold, one of the parameters that records is the temperature. So that's one way to determine that and to be able to sort your images in a library if you don't have a program that will do that for you automatically. Another example, a really great program, I use this all the time when I'm shooting DSLR images with my computer, is I use Backyard EOS, or Backyard Nikon is the companion for the Nikon cameras. This was developed in Ottawa, and one of the things that it allows you to do is to format the file name of the image that you take. And one of the parameters that it allows you to input, if you want it in your file name, is the temperature of the sensor. So here, in this example, I was shooting M17, 60-second exposure, ISO 3200. I was shooting it at f10, the time that the exposure started, and the temperature that the sensor was at when it took that exposure. That saves you a lot of legwork, and again, allows you it saves you time in terms of having to probe into opening headers and things like that to get out this information. As I say, some of the high-end programs will do this for you automatically because they also read the XF info. and they can sort by that. All right. So just to give you some examples of the effect of this dark noise reduction, I'll just show you in these last few slides there what you can see. I should mention too, one of the things that I showed you, the three types of noise that we can deal with, you know, the bias level and our dark current. The bias level is basically the noise generated by just your camera operation. Theoretically, it's like a zero length frame. Obviously, that's in an ideal world. So it's the shortest exposure you can take at the same ISO. But that information, that noise that's generated by that operation is also embedded in your dark frame. So if you do have a set of darks that are at the same temperature as your light frames, you don't have to do a bias calibration. When you subtract the darks, you'll also subtract the bias. If, on the other hand, you're using dark frames that are at a different temperature than your light frames, then you'd want to shoot bias frames to be able to scale them. The programs that will handle that, as I showed you down in that list, will take that into account. They'll use the bias frames to scale the darks to match the difference in the temperatures with your light frame. Hopefully that makes sense. All right. Oh, and I wanted to mention too, I recently completed actually a manual for Doug George and his new generation of SPIG cameras, the Illuma cameras. And if you want to download that manual, it's a free PDF on the SPIG website. You can either do spig.com or diffractionlimited.com. Just ping on the Illuma cameras, and under the product descriptions you'll see downloads, and you can download the user manual. So I wrote that, and there's a lot more of this descriptive information than I have time to deliver here tonight. I mean, most of the manual deals with obviously the camera itself, but Chapter 3 is a more general treatise on image calibration. So there I talk about dark fields, flat fields, and bias frames in more detail than I can offer you tonight. So free download if you want to grab a copy. So this, again, just to show you the effect of what the dark frames will do. This is the one I showed you previously. This is a single dark frame with its histogram boosted to show you the pattern noise. That is a stacked dark frame. I'll go back and forth a little bit, and you can see this one looks somewhat noisier, and the pattern itself isn't as distinct, whereas you can see by stacking it, stacking a dark does the same thing as stacking a light frame, is that if there's a consistent signal, which is the pattern noise, it'll start to build that. And when that is built up higher to higher levels, it's more effective in removing that from your light image when you do a subtraction. Okay, so that's a stack. Did I have there a stack of, I think, 8 or so on that one? That's what the temperatures that I had. So if we take that, this is and actually, can you dim the lights there a little bit there, because some of the details in the next few slides are subtle. I don't mind being totally in the dark. I'm told I'm like that all the time. Hello, Robert, Earth to Robert. Dim the lights. Okay, I'll do it. Thank you. All right, so this is a single field. It's actually I combined my observation image for this evening with this talk. So this is a single light frame, and basically that's what came out of the camera. There's no processing here at all. If I zoom in on that area there, it's about a 400% magnification. Again, single dark frame. So you can see that there's stars there, and there's a background there, but the background has some modeling in it and stuff like that. Part of that is the noise that we're trying to deal with in the dark frame. So if I take this dark frame, or if I take this light frame rather, and subtract my dark frames from it, you can see what's happened there. And again, on some images this is very noticeable, on other images not so much. It really depends on the camera and the conditions you've shot them. So I'm just going to toggle back and forth, and you can see what I subtracted. That's the single image, and that's the single image with dark frame subtraction. This also becomes important when you stack your light frames. In other words, when we take these pictures, we don't usually just take one image unless it's a moving phenomenon. We like to stack images. So what we want to do is we want to take the dark frames, we want to get a collection of them, and turn them into a master dark frame. Because this will help to eliminate random noise as well as the pattern noise. And then when we take that, we apply that master dark frame to each of our single frames before we stack them. So it does a very effective job on removing some of that extraneous noise. And what you get is that. So you can see a lot of the modeling has gone away. A lot of this being caused by random noise. And then again, I'll just flick back and forth. Much smoother to work with. A lot of the little tiny pixel-to-pixel color aberrations have gone. And again, those aberrations, it's not a defect in your camera, it's just the nature of the beast. So by producing a stack of images, each of which has had a master dark frame subtracted from it, you wind up with a truer representation of what it is you're trying to shoot. And also it's cleaner in terms of the inherent noise in the image. So it gives you a much better starting point for your more elaborate processing. All this stuff, this calibration, it's also referred to as pre-processing, because once you've got past that step, then you can go to town with any of these programs like Photoshop or Maxim or PixInsight or whatever to do your fancy calibration, boosting your levels and everything. Because you have a better signal to noise ratio after you've done this pre-processing, you have more latitude to play with on those subsequent adjustments which give you your final image. So it's well worth doing. And just to show you the final result, that's what I did with this. When Oscar asked me to do this, I thought, well, I'm working on an image for tonight anyway, so I'll just save some of the intermediate steps, which I usually discard. So what I did is I processed the set. This is the Fll Nebula, by the way. I processed the set, which is 18 images, and did the exact same post-processing, the fancy stuff, to the uncalibrated set, in other words, the set that didn't have dark frames subtracted, as I did to the dark frame subtracted set. And you can see the difference. Again, it's not dramatic in this one, but what you can see, and especially on the screen there, it doesn't show it nearly as well as on my monitor. But what you can see is when I'm flipping back and forth here, this is the one that has the dark frame subtracted. It's a higher contrast image because we've suppressed those dim pixels, that patterny noise that was in there, and it gives us again better signal to noise ratio, better contrast. The stars pop a bit nicer, and there's definitely better detail on the boundaries, on the edge boundaries of the nebula itself. So that in a nutshell is dark frame subtraction. Give it a try. As I said, download that manual if you want, because there's several pages of that in chapter 3, and then it goes into a lot more detail of how these various forms of calibration interplay with each other. I didn't touch at all tonight on shooting flat fields, which is another form of calibration. I talk a little bit about it. Well, I talk a fair bit about it in the manual there, but hopefully at a later point I'll do a follow-up to this, and we'll talk about flat field calibration. Thank you very much.
Alrighty, thank you, Paul.
You're welcome.
We're going to go to break in a moment, but before we do, I think Rob, Dick wanted to say something.
Very brief. That's what I promise. Twice a year, I invite people to my observatory. And it's got a 24-inch Newtonian Cassegrain, and it's located out near Rideau Ferry. And if you're interested in coming out, see me afterwards. Or what I'm also going to be doing is I'm going to be sending an email out to the membership saying, if anybody's interested in coming, you need a map, send me your email, I'll send a map out. There is usually observing on the Friday night, observing on the Saturday night. However, we go to dinner on Saturday night, so if you've got some money burning in your pocket, we go into Perth to a restaurant, have dinner, get back to the observatory around 8 or so, and then we observe till the moon rises. And if you're interested in coming, just contact me and respond to that email that I'll be sending with the members list, or see me tonight and I'll give you my email and you get a hold of me. And it's going to be on the weekend of the 13th, 14th of July, so it's in about a couple of weeks. So by all means, if you're interested, please give me a call.
We're going to go to break now. There's door prize tickets here, and I'll find a victim to give them out. The door prizes are all out front here. I don't know about this camera or speaker. Do they belong to anybody, and are they?
Yeah,
door
they're
prizes?
door prizes.
They are door prizes.
That's for door prize, and the white bag beside it is a set of computer speakers, and they're both up for bid.
Awesome. Great. Thank you. All right. We'll reconvene in, let's say at 8:45. Okay, so I guess as part of the 150th anniversary of the Royal Astronomical Society of Canada, the Royal Mint put together this $1, $20 pure silver coin that actually has a fragment of a meteorite in it. It's pretty cool. I think it's on sale at the Mint for $150. But it's totally sold out. I went to several postal outlets trying to get one.
Oscar, did you start the camera?
I did not start that camera, thank you. Now I got to do that whole spiel again, I guess. Yeah, so if you manage to get your hands on one of these, you're a lucky person. I guess he only produced 5,500 of them. Are the mics on, Rob?
Yes, they
Yeah, okay. I guess some stamps were also produced by Canada Post. There's the souvenir pamphlet, and there are the two stamps featuring the Milky Way and the Aurora Borealis.
I got him.
I've got mine on order. All right, so we're going to start off this half with Simon, who just conveniently walked in.
Yeah.
You click right here?
Oh, you want?
Yeah. Big green button advances, red button goes back. There's your place.
So if we can leave the lights on over me, you can do whatever you want with the lights over everybody else. Although you can leave the lights more or less like this. All right. So in my first talk in this series on rapidly evolving solar system science, it was entitled Origins. And if you missed it, you can find it on my website. You'll see the URL in just a minute, under Planetary Geology / presentations. And it contained 3 parts. So I've got to press this. Maybe I've got to press it that way.
No, the big green button goes forward.
That's the big green flashy button. Oh, I see.
That's the laser button.
The really big button. Oh, I was actually hitting you with a laser button. I'm going to get arrested and funny.
You have your checkbook?
Yeah, actually, I've got my credit card. Okay, so there's the URL for the last month's presentation. First, I presented an overview of what has become the new standard model for the origins of the planetary component of our solar system, from the solar nebula to planetary accretion, and eventual migration of the giant planets. And I pointed out some of its major weaknesses, one of which is the difficulty of explaining the time gap between the first 100 million years after the formation of the Sun and the supposed late heavy bombardment some 600 million years later. The second weakness was a key integral part of the model is the initial accretion of primordial dust to form the first grains of rocky material. And I highlighted how poorly we understand how nature overcame the multiple barriers to accretionary growth beyond the size of dust and sand grains. That's quite a barrier. Now, some scientists believe that turbulence in the primordial accretionary disk helped to overcome some of these barriers to early accretion, which brought us to the third part of the talk, the behavior of gas, dust, and solid particles in the accretionary disk, and how the disk's behavior may have been governed by its viscosity. But I pointed out that we have no way of knowing how that viscosity was distributed in space or how it evolved in time, which means that the large-scale models of accretionary disk behavior and structure are dramatically oversimplified. And there's simply nothing we can do about it. Now today, I want to return to the issue of accretion from dust to planets. Now you recall that the classical model of solar system formation states that somehow dust turned into gravel-sized chondrules of rocky material that clumped together to form pebble-sized objects, that then further clumped together to form asteroids, planetesimals, planetary embryos, and eventually the planets themselves. Now the operative word here is somehow, because there's a great deal of debate about this, especially regarding the formation and the significance of what are called chondrules. And that's what we're going to look at today. And these, well, no, that was not what I wanted. Go back, there we go. These things here, these round objects here, those are the chondrules. It comes from the Greek for the word rice grain. Now here's the spoiler. Today, this accretionary time sequence from dust to chondrules to planetary bodies appears to be wrong. And we're going to look at why. Now, in my first talk of this series, I presented this list of 5 fundamental headaches confronting professional planetary scientists trying to understand solar system formation. And tonight we're going to go back to number 2, but with a slight change in wording. How did chondrules form? Now, the formation of chondrules is one of the fundamental questions regarding planet formation. If we don't understand how chondrules form, we can't work out how planets and the entire solar system form. Now, according again to the classical view of chondrule formation, dust in the accretionary disk sticks to other dust by electrostatic forces, and it ends up forming dust bunnies that essentially get flash melted by some form of energetic shock, such as solar storms, the sun, or electrical discharges in the accretionary disk. Now, according to this, the classical view, chondrules were formed before accretion, and therefore they represent the fundamental building materials of asteroids and planets. However, we've known for decades that there are major problems with this model, not the least of which is the very common presence of well-formed crystals of silicate. That's these things here, inside this circular object. And you can see that these things have well-formed, well-shaped tips. So these are well-formed crystals of silicate or rock-forming minerals as inclusions in individual chondrules. And this, through the microscope, is an individual chondrule. That's probably, maybe that thing might be a ½ centimeter across. And those well-formed crystals of silicate could not have grown in the gas and dust of the primordial accretionary disk. In order to achieve the size of these things, several millimeters at least, and their shapes, which is key, the included crystals needed time to grow. Time to grow. Within a slowly cooling magma before the chondrule formed and included them. And that can only be achieved in a slowly cooling body of magma within an already formed planetary body. In short, chondrules cannot have formed before asteroids and planetesimals, at least not before all of them. Okay, so if the classical model of chondrule formation by accretion doesn't explain what we can observe in nature, and this is not a this is not a drawing, this is a photograph. If it can't explain what we observe in nature, where do we go from here? First, let's take an overview of the primary observational evidence, and then let's look at what the professional astrophysicists are up to. And what they're up to is computer modeling. So let's start with meteorites. Meteorites can be classified according to two schemes. One's simple and one's more complicated. So the simple scheme talks about chondrites, or chondritic meteorites, as well as, and that's what this would be up here, as well as stony meteorites, or stones they're sometimes called, or iron meteorites. And those stony and iron meteorites are called achondrites. So you have chondrites and achondrites. And as I told you in a pair of talks 15 years ago, yeah, it was that long ago, I'm afraid, and the URLs for those talks are down there. That's why I already have all this white hair. Chondrites represent the most primitive meteorites whose chemical composition corresponds to that of the original solar nebula, minus the gas, hydrogen and helium essentially. On the other hand, the achondrites, especially the stony and iron meteorites, they represent rocky crusts and the iron-nickel cores of planetary bodies that melted, differentiated, and then broke up during asteroidal collisions. And here is a Mickey Mouse cartoon of a differentiated planet with a crust out here in brown and beige. There's the core, and then in there in the green is what's known as the mantle. Now, curiously, there are not many examples known of meteorites that represent the volumetrically dominant mantle rocks of differentiated planetoids, but that's another story for another time. The more complicated scheme of classification of meteorites divides meteorites into groups, principally classified according to their chemical and then mineral composition. Now, there are between 100 and 150 such groups, depending on who you talk to. But each group represents a different parent body, a different planetoid, that shattered during a collision, most commonly a collision that's supposed to have occurred early in the solar system's history. Now, here's the important part. On the one hand, only about 1/5, 20%, of the parent bodies is chondritic. In other words, what the classical story would consider to be primitive. The rest, 4/5 of the parent bodies, melted thanks to the accumulation of heat from radioactive elements contained within them and differentiated, as you see here. This means that the vast majority of early planetoids were internally hot. This is going to be very important in just a minute, so keep it in mind. On the other hand, chondrites account for 5/6 the number of meteorites, as distinct from the groups of meteorites, the number of meteorites, which means that the formation of chondrules was a process that affected a substantial fraction of the solid material in the solar nebula. In short, it was an important process that we need to understand. So what exactly are chondrules, these things inside this chondritic meteorite? They are grains of magnesium-rich silicate minerals, olivine and pyroxene for those who want to know that kind of thing, that make up about 50% or more by volume of a chondritic meteorite. The rest, the matrix that sticks the chondrules together, was originally glass mixed with organic carbon. Now, the chondrules formed by the cooling and solidification of droplets of silicate liquid, in other words, magma, molten rock material, that chilled in space, in the cold of space, in a matter of hours, according to laboratory experiments. Okay, this much appears pretty straightforward, except that it does not allow enough time for the well-formed crystal inclusions that we just saw in about 2 slides back. And it doesn't allow enough time for those crystals to grow. And droplets of silicate liquid floating in empty space should chill in seconds, not hours. More on this later in the talk. Now, classical theory says that clumps of dust in the solar nebula were transformed directly to chondrules by rapid melting, probably as a result of shock-induced heating of some sort. Where does this idea come from? First, because of the remarkable similarity between the chemical composition of the chondrites and the sun's photosphere, except for the gases, hydrogen, helium, etc. And since the sun's composition is the same as that of the primordial solar nebula, for the most part, chondrules are supposed to be primitive. And second, because things called calcium aluminium inclusions, these, that one there, that one there, that one there, the white bits in here, those are considered to be calcium aluminium inclusions. They occur as inclusions both in the chondrules themselves and in the matrix of the chondritic meteorites. And this was considered to be important because by convention, in other words, as an assumption, the calcium aluminium inclusions are taken to mark the beginning of time in the solar system. They are considered to be the first bits of something solid. And they were interpreted to form in the same way as the chondrules, but just before the chondrules formed. That's the classical story. Now, according to this model, after initial accretion, some chondritic planetesimals became overheated, melted, and differentiated into metal cores, basaltic crusts, the sources of iron and stony meteorites, the achondrites, as I've already said. However, as we've already seen, with the well-formed crystal inclusions within the chondrules, this entire story has now been called into question. In addition, there are now major issues with finding a heat source for flash melting dust clumps in space. Many heat source models have been proposed based on the idea of solar wind, electrical discharge heating, electromagnetic radiative heating, gamma ray bursts, and heating in protostellar jets. But they all seem to have insurmountable problems. The currently favored nebula shock melting model invokes bow shocks around planetary embryos plowing their way through the gas and the dust of the accretionary disk, rather like a ship plowing its way through water. But it doesn't explain the physical diversity of different chondrules. I'm going to be talking about these in more detail in a moment, but if you look at these two chondrules here, they're physically quite different. What they contain internally is different, and their exterior is different. This one here has a rim, which is similar to this rim, but it's got a second rim around the outside, made of much smaller grains. We'll come back to that. So the thing is that this nebula shock melting model doesn't explain this diversity of different chondrules. However, if chondrules formed via processes involving already formed planetesimals, then we would have to see them as a byproduct of planetesimal and planetary formation, rather than as a precursor, and this would be a completely different ballgame. So let's now look at this new ballgame, a game that the professional astrophysicists are currently playing by computer modeling. Why? Because there's no other way to do it. Back in about 1980, a new hypothesis suggested that many chondrules are in fact frozen droplets of spray. Spray from impact plumes launched when thin-shelled, hot, largely molten planetesimals collided during accretion. And that's what this is trying to show here. These are two different views simply of the same thing, where here you're measuring, where's it? Oh, here we go. Here we're measuring pressure, and here we're measuring density. So it's just an illustration of what happens after a collision and that spray going off into cold space. Referred to as the splash hypothesis, this wasn't taken very seriously until computer simulations in 2011 showed that it was possible, at least theoretically. Now, the key to understanding the modern version of this model is the role of radioactive elements responsible for heating the early planetesimals. Specifically, an isotope known as aluminium-26, which has a very short half-life of only 0.7 million years. You compare that with the billion-year plus multiple billions of years half-life for uranium. Its half-life is only 0.7 million years as it radioactively decays to magnesium-26 and generates heat. This means that the early planetoids were only heated internally by aluminium-26 during a short time window, about 2.5 million years, with a maximum heating and melting window at about 1.5 million years after calcium-aluminium inclusion formation. In other words, after the beginnings of the solar system. So according to the splash model, the chondrite meteorites that we find today do not come from collisional breakup of the earliest planetesimals, as the classical model states, because the early accreted chondrules would have been destroyed. Destroyed as those early planetoids, which they formed, were heated by aluminium-26, melted, and differentiated. Instead, chondrite meteorites are made of material that accreted later, when aluminium-26 had radioactively decayed to the point that it could no longer induce the melting of planetoids. So, okay, just exactly how does this splash model of chondrule formation work? At least in the computer simulations, because that's what we have. Imagine a young solar nebula heated by aluminium-26. Most of the material existed as molten or partially molten planetesimals for the first 2 million years after calcium-aluminium inclusion formation. In other words, the first 2 million years of the solar system containing solid materials. These largely molten spheres of primitive magma were undergoing turbulent convection in internal magma oceans, each enclosed within a thin shell of rigid crust. And here you can see a nice linear drawing. There's a core, there's a crust around the outside, and here's the internal magma ocean, and you can see the idea is that it's stirring as it's convecting. Here's a fancier picture representing exactly the same thing. According to the computer models, collisions between planetesimals would have launched huge plumes of molten droplets, in other words, spray, from the internal magma oceans, mixed with loose material from the planetesimal surfaces. And that's what these are taken to represent in these models. I'm not going to get into the details. This is here by way of an illustration for you for the moment. It's model collision scenarios. Oh, and these would be the impactors, and this would be the target. So in all three cases, which we're not going to step through. We don't need the details. However, most collisions would have been oblique glancing blows in which the smaller body, the projectile, would have been engulfed by the larger body of the target, while the overshooting portion, and that's what this would be here in all of these scenarios, would have undergone catastrophic decompression in space and expanded slowly downstream as a huge fan-shaped plume of droplets and debris in nebulous space, where the droplets would chill or quench to form chondrules. Why are astrophysicists so keen on hot or molten planetesimals? Think about it. In order to melt something, you need energy to transform to heat for the melting to occur. In the early solar system, the obvious energy source is the kinetic energy of motion during asteroidal collisions. However, the colder the starting temperature of your colliders, the more energy you need to convert to heat, which in turn requires higher speed collisions to provide all that energy. High speed collisions present a problem, as we'll see. Equally, the converse is true. A hot planetesimal heated by aluminium-26 only requires a small collisional energy to be input in order to melt, which translates into relatively slow collisions between impactors and targets. Now, by introducing slow impact speeds into their models and injecting the melts in the models produced by the impacts at speeds that approximate to the asteroidal escape velocities, in other words, just around the speed that the material would need to actually escape from the collider or the target, the spray of molten magma generated by a collision doesn't go very far from the target. Go back. There's my collision occurring, and here are my chondrules derived from the spray, and you notice they're not very far from the relic core of that impact. Then there's two ways it can go. We won't get into the details. So most of the chondrules from the ejected melt spray will quickly fall back onto the surface of the target asteroid or the collider rather than flying off into space. And that's what's illustrated here. Here you can see the chondrules coming back onto the surface of either the collider or the impactor. It's the same thing is happening here, a slightly different scenario. Now, this is a very attractive numerical model for chondrule formation, but does it explain tangible observations that we can make in real samples of meteorites that other models cannot explain? And the answer is yes. So let's quickly look at 4 examples, 4 of the simpler examples of observations that this can explain, and we're going to skip the complex isotope chemistry for today. This is one of the chondrules that I'd shown you earlier. First, some chondrules in some meteorites have a recrystallized outer rim. So here's the inner part of the chondrule. We won't worry about what's in there for now. There's the inner part of the rim of the chondrule, and this outer part of the rim here is made of all these smaller crystals. Look at that pink one there, which is quite distinct from this blue one here, quite distinct from this yellowy, greeny, bluey one, etc. According to the low impact velocities of the splash model, chondrules would have fallen back onto one or other of the colliding bodies, forming part of the rigid crust, underlain by the convecting magma ocean. The splash model would explain these recrystallized rims as either the product of remelting and recrystallization of older accreted chondrules due to the heat of a new, younger impact, or as new rims crystallized on old chondrules that got entrained into the underlying magma ocean prior to being ejected yet again and again in a later impact event. Here are our well-formed crystal inclusions, as we've already seen. Many chondrules contain these perfectly formed coarse crystals as silicate minerals. The splash model suggests that the coarse crystals, that's to say, these things here, the inclusions, with their nice shapes, were formed within the convecting magma ocean and were subsequently ejected into space with the molten magma during asteroidal collision. In short, when planetesimals meet and collide, they eject a plume that contains older, well-formed crystals and fragments of crystals, which end up as inclusions in the droplets of molten rock from the internal magma oceans that form chondrules in the bulk of the plume. In our third example, some chondrules in some meteorites have mutually indented shapes. You can see that here. Look at that chondrule there. It's actually indenting into this chondrule here. It's pushing up against that one, and it's actually pushing into this one too. And if you look at this example, this small area here with all these chondrules all the way around, this small area has been blown up, and again, you can see that this chondrule here is pushing into this one. This one's, actually this poor chondrule here is having a hard time. This area here is pushing into it as well. This chondrule, with its inclusions, is pushing into all of these. And that one is pushing into this one. So they're molded against neighboring chondrules, indicating that they were still hot and plastic, if not liquid, when they came into contact. Now, sometimes these molded chondrules form clusters, indicating that they came together as a group of hot and plastic chondrules that then became welded to each other. Now, according to the low impact velocities of the splash model, chondrules would have fallen back onto one or other of the colliding bodies, piling up on the surface and getting squished under their own weight while still hot and plastic. And our fourth and last example that I'll show you here, or observation that I'll show you here, is that many chondritic meteorites contain chondrules of many different types and many different compositions in the same meteorite. That's what's happening here. This is one chondrite example, and this chondrule here looks nothing like that one, looks nothing like this one, looks nothing like this one, and they're all of different compositions, so how do you do that? The splash model explains this as a direct consequence of plumes of mixed materials from multiple, successive, chondrule-forming impact events involving multiple different asteroidal bodies. In addition, it offers a neat explanation for the presence of chondrules and quenched glassy matrix, or chilled glassy matrix, altogether in a given chondrite meteorite. There is a fifth issue that the splash hypothesis may resolve. Why do laboratory results predict that chondrules took hours to chill, but numerical models predict quenching in seconds? According to the splash hypothesis, the close spacing of the magma droplets in the dense ejected collisional plume provides thermal insulation. And that thermal insulation slows the cooling rate of the droplets compared with the cooling rate of an isolated droplet in the cold of open space. That's pretty neat in my opinion. Okay, so far so good. It seems like we now have a viable model for the creation and accretion of chondrules to make chondritic asteroids and meteorites. Or do we? Well, in 2017, a group of planetary scientists pointed out that if the planetesimals involved in the splash model for chondrule formation were truly molten in the interior magma oceans, or with interior magma oceans, there are consequences. Consequences for the chemical and isotopic composition of the chondrules. Those consequences are too detailed for us to get into here. The thing is, we don't observe those chemical and isotopic complications. To get around these issues, they suggested that the planetesimals were almost, but not quite molten. Essentially a minor correction to the overall splash model for the formation of chondrules and chondrates. So, yes, after all these years, we really do seem to have a viable model for the formation of the all-important chondrules during the early history of the solar system. The take-home message for this new splash model is that most achondrite meteorites, the ions in the stones, now appear to have come from planetesimals that had accreted, melted, and differentiated rather early in the solar system's history, within only 2 million years after the formation of the calcium-aluminium inclusions, which are taken to represent time equals 0. Once aluminium-26 had decayed such that it could no longer induce the melting of planetoids, chondrules could begin to survive, which means that the chondritic parent asteroids were assembled later than 2 million years after calcium-aluminium inclusion time. In other words, after the first 2 million years of solar system history. Put simply, chondrites, far from being the first planetoids to have accreted in the solar system, as is conventionally assumed, were likely among the last. So where have we come to in this overview of rapidly evolving solar system science? In the first talk of this series, we looked at the structure and the behavior of the accretionary disks and how they influence accretion from dust to sand grain. That's what we were looking at here. And if you missed that talk, this URL here can take you to my website and to that presentation. Today we've re-evaluated the place and the role of chondrules in the formation of early planetoids. Next time, we'll tackle the issue of planetary migration. In other words, we're going to take a look at the most recent thinking about the migration of the giant planets and the unsettling 600 billion year gap between their inward migration and their outward migration that purportedly provoked the late heavy bombardment at about 3.9 billion years ago. And we'll look at whether or not it even happened. As always, thanks for listening.
All right. So next up, we've got our observation reports. So if you've submitted observations, kindly make your way to the podium. You're up first.
So I use a Malin cam.
Sorry, just a second, Jim. Rob, can you dim the lights down, please?
All right. So I use a Malin Cam Exterminator 2, which is a very sensitive video camera with a Celestron 8 Evolution, Smith Cassegrain, and Miloslick software
So I'm getting a live image refresh on the computer screen depending on the exposure time, which for this camera is very, very short, seconds most of the time. The software, MiloSlick, receives the image from the camera and improves the signal-to-noise ratio on the fly with live stacking, histogram, using dark frames to help with that, along with other control features. So because of the fairly immediate visual feedback of this setup, it can be used as an outreach educational tool as well as for astrophotography. So this image here is a 10-second exposure of M57, or the Ring Nebula, in the constellation Lyra. And as you know, M57 is a planetary nebula which represents the last stage of in the life of a dying star that has exhausted all of its hydrogen gas for fusion and eventually swelled into a red giant star, expelling its gas into space before becoming a hot, dense white dwarf star that we see right in the middle of the image, which would be right there, is the white dwarf. And the heat from the white dwarf excites or ionizes the gas around it, which results in giving off photons of light of different wavelengths depending on the type of gas that's being ionized. So one source indicates that the hot blue gas near the white dwarf itself, you might not be able to make out the blue, is said to be ionized helium, which gives way to cooler green and yellow gas, ionized oxygen. And at greater distances, we see the cooler red gas, ionized nitrogen and sulfur, along the outer boundary of the Green Nebula, of the Ring Nebula. The gases are expanding outward at 30 kilometers a second, and will do so for another 10,000 years until it fades completely. The diameter of M57 is 2.6 light years and is approximately 2,300 light years away from Earth. Okay, the next image is a 15-second exposure of M82, better known as the Cigar Galaxy in the constellation Ursa Major. And the Cigar Galaxy is known as a Starburst Galaxy because many stars are being born there at one time. It's about 5 times more luminous than the Milky Way, and it is approximately 12 million light years away. Okay. This is a 16-second exposure of NGC 4565, better known as the Needle Galaxy, and it is an edge-on spiral galaxy approximately 30 to 50 million light years away in the constellation Coma Berenices. So I have 2 images here of M87. M87 is a supergiant elliptical galaxy in the constellation Virgo. This is a 12-second exposure of M87. This galaxy is one of the most massive galaxies in the neighborhood. Its total mass is approximated to be 200 times that of the Milky Way. And at the core is a supermassive black hole which forms the primary component of an active galactic nucleus, or AGN, which yields a very strong source of radiation believed to result from the accretion of matter by the supermassive black hole at the center of this galaxy. Jets of energetic plasma originate at the core and extend outward at least 5,000 light years. So these jets are traveling close to light speed, and they're traveling along the axis of rotation of the black hole. Now you may be able to see a horizontal jet forming at 1 o'clock. So what I decided to do when I saw that, I took another exposure, a 20-second exposure of M87. And I think you can see the jet a bit better right there. So that's the story. Thank you.
Very nice.
Thank you.
Okay, so kind of have a couple observations I took back late May. This is the Sunflower Galaxy M63 in the constellations Canis Venatici. It is about 27 million light years away, and it's, as far as spiral galaxies goes, it's one of the most attractive, with a lot of interesting internal detail that resembles a Fibonacci sequence. It was only about 25 minutes of total integration time with 5 minutes sub-exposures, but I did manage to pick up a fair number of other faint fuzzies off in the distance there. So I do intend to revisit this at some point. And then a few days later, Dumbbell Nebula. These were both taken at Fll on a subsequent evening. I was there with Paris and Gordon. And wow, this one really surprised me when I pulled out the reds of the hydrogen alpha. In total, was 14 5-minute exposures for a total of 1 hour and 10 minutes. And the full suite of calibration frames that we heard about this evening, including darks, bias, flats, and dark flats. Yeah. So in the center, you can observe the white dwarf, the core of the remnant star, and it's a fine example of what may, in our future, could happen to the sun. And I think you can also see some of the really faint halo that is really, yeah, okay, that's all. Thank you.
I wanted to show the cat's eye. So I took this picture of the cat's eye, and it's pretty pathetic. So I decided to look it up first. It turns out to be about 20 arc seconds across. And my field of, that's 1/90th of a full moon. And my field of view here is about a full moon, maybe a little bit more. So let's just look in a little tighter. Oh, and to get a little better, I whacked a Barlow on my telescope. And I use a Newtonian, and Barlows and photography don't work well together, but maybe you get a little closer. So anyway, we got to that, and now you can really see the cat's eye. It's about 3,300 light years away. And interesting enough about it, it's expanding at 10 milliarc seconds a year. How you'd measure that, I don't know. But it means it's about, so if you collapse it backwards, it's about 1,000 years old when it blew up. Okay, let's go back to the original image here. By the way, see the slightly darker frame? That's the Barlow image superimposed on it. The big frame is outside of that. We talked there earlier, you saw earlier today about taking an image and stretching it. So what you do is you take the gray part of the image and you make it really, you suck it higher, basically. And we can see more. And so those are the same images, except I sucked it up a little bit, the light gray area. And now you can see the cat's eye in the middle, but you can also see that there's been a halo blown out earlier. And you could never see that visually, but it's there. And if you want to look a little tighter, this is just a crop. That's what it looks like. And if you look at the sky, you'll see all that noise that Paul was talking about. That there's not enough exposure here. Oh, by the way, I love those 8-second shots. Wow, I spent like hours instead of seconds. Those are incredible. All right. Next one was the sextet, which is kind of interesting. It's about 190 million light years away, so it's pretty far away. And it's six of them, but there's only 5. And so again, I whacked the bar a little bit. It got a little closer. I went into this, and all you're really seeing is a fuzzier picture. There's not much more detail in this, but you can sort of see that there are 6 galaxies, actually 5, and one of them is a split. And then, all right. Did I jump over one? No. Good enough.
Did we miss one?
You missed one. Something, doesn't matter.
All right, next one.
Thank you very much.
All right, time for the observing challenge. If you recall, last month I had MA for the beginner challenge, the Cat's Eye Nebula for the intermediate challenge, which Bob got. The advanced challenge was Safer Sextet, which Bob also got, and I had Schroeder's Valley as the lunar challenge. This month, we're going to start with Alberio for the beginner challenge. So that's the double star in Cygnus. It's right on the end on the tail end of the constellation there. We'll do the Trifid Nebula as the intermediate challenge, or M20 in Sagittarius. We'll do the Elephant's Trunk as our advanced challenge, which is IC 1396. And we'll have Gassendi as our lunar challenge there. And thanks to Bob there for suggesting those deep sky challenges for July. There they are again. Anyone needs to write them down.
Also, you can add to the Alberio challenge that the people have to identify the 2 colors.
Yes. All right, Fll Star Parties. So there's one coming up on the 14th of July. It looks like the June 9th and May 12th ones were a go, and hopefully we'll have cooperative skies for the 14th, which is my birthday, so I won't be going to the Star Party. I'll be doing something else. There's always sorry. We're also having the Star Party at the Defen bunker there. Sorry, I got lost here. Did I get those dates confused? No, those are the members on the Star Party. All right. Yeah, normally we have our public Star Parties at the Defen bunker. The next one, it looks like, is the 13th of July, so the day before. I may attend that one, we'll see. With the rain date of the 14th of July, 20th of July, 21st of July. Tonight and tomorrow night, there will be sidewalk Star Parties at the Cube Gallery in Westboro. I think Mike Mugdam is organizing that, which is cool. And Chuck O'Dale is giving a talk tomorrow at the Cube Gallery. So it's a good time. They get the lights turned off around that street, which is neat. All right, the library, Stell's Pick of the Month, The Universe Within, by Neil Turok. Here are the folks that help operate the club. Let's give them a hand. And our meetings are available, our meeting recordings are available on our website. We had 107 people attend today, so thank you for coming. We'll have our post-meeting meeting at Grace O'Malley's just on Ogilvie Road. And our next meeting is August 3rd. It is a long weekend. Normally we push them out to the second week when there's a long weekend involved. But that second weekend is Starfest. So we're going to hold it on the weekend. We'll hold our meeting on the weekend of the long weekend, August 3rd.
Isn't it something else too?
Is it something else, Gordon? Yeah. No, I'm not sure. The other thing is, I'm going to have a slightly shorter program for the August meeting. I'm hoping to do some observing, have people bring telescopes, and we'll do some observing after the meeting. Maybe we'll aim to adjourn the meeting at 9 o'clock next month. I got to clear it with the museum, so stay tuned. I'll send an email out inviting people to bring scopes if that's going to be the case.
Okay, it'll be cloudy.
That'll be the other thing.
Say it too loud.
Member benefits, if you join, you get access to the Ted Binlow Library, the Stan Mott Book Library, and the Fred Lossing Observatory. You also get access to some spectacular publications. All right, and it's time for door prizes. So my understanding is that these telescopes are also up for grabs. There's 2 scopes here.